Okay, let's study some more about the graphs of the trig functions sine and cosine. I hope you will notice on your worksheet that we are going to study the graphs of, I'm going to go ahead here, it says y equals a times the sine of bx today. So I'm going to be adding a coefficient in front of the variable x as we study this topic. I think what I'd like to do is I'd like to go to a blank page and just do a little bit of a review. So remember, please, when we graphed y equals just the sine of x. So let's do that first. Y equals the sine of x. We found that when x was 0, y was 0, and that when we got to 90 degrees, which was pi over 2 radians, then the sine of 90 degrees was equal to 1. And then we went to pi radians, which is 180 degrees, and the sine of x was 0. And then we went to 1.5 pi, or I called it 3 pi over 2, and the value for that 270 degree angle for y, the output would be a -1. And then finally we got back to where this wave repeats again, and at 2 pi radians, or 360 degrees, the sine of that is equal to 0. And then we also found some points in between so that we could see that nice wave that occurs for the graph of the sine of x. Please remember that this goes on in either direction. What I'd like you to notice in this problem is two things. The period, or the time it takes for this function to get back to where it started, from here back to where it started so that it goes up again. The period of this function is 2 pi, or 360 degrees around the circle. The next thing I'd like you to notice is that a sine curve starts at 0 and it goes positive through the first quadrant, stays positive through the second quadrant, then it goes negative through the third and through the fourth, and then we're back to a coterminal angle. We're going back around the circle again from 0 to 90 degrees right here. So you need to memorize that the sine of an angle starts at 0, 0 and then repeats, in this case at 2 pi radians. And then next, just remember, and I'm going to put this right down below, that the cosine of x, if you looked at a 0 degree or 0 radian angle, the cosine of 0 is equal to 1. But at 90 degrees, or pi over 2, the cosine of that is 0. So cosine is positive in the first quadrant, like all the trig functions are. Then when you get to 180 degrees, this is the second quadrant, the value for y is a -1 at pi radians, or 180 degrees. So cosine is negative in the second quadrant. We go to 1.5 pi, or 3 pi over 2, and the cosine of that is 0 again, so we bring that wave back to the x-axis, and then finally at 2 pi radians, I'm back to where I started, and the cosine of 2 pi is the same as the cosine of 0 because they are the same angle. And then this is the period again of y equals the cosine of x. So I'm just going to go ahead here and call this y equals the cosine of x. So the period of that function is also 2 pi. Remember that it goes on as well, and I'll just try to exaggerate that a little bit, in either direction. And please notice that this cosine curve is just the sine curve shifted to the left 90 degrees, if you will, or pi over 2 radians. But a couple of things that I just want you to really understand here is that the period is 2 pi when the equation is just y equals the sine of x, or y equals the cosine of x. The period is 2 pi. Because now what we're going to study, and I got to see if I can go get this. Sorry, there we go. Now what we're going to study is y equals a times the sine of bx. And you know, actually, I'm going to go back again one more time. I forgot to state, as I was reviewing with you, that when I put a numerical value, wanted that to be a straight line, when I put a numerical value in front of, and so let's do this for let's go ahead and call this y equals 2 times the sine of x. So the curve looks the same now for the sine curve, but this represents the amplitude of that curve. So now sine starts right here at 0, 0, but at pi over 2 radians, the value for y is going to be 2. The amplitude is going to be 2 for this curve. Before it had a 1 times the sine of x in front of it, but we didn't write the 1. We just wrote that as the sine of x. That's all we did. Was write it as the sine of x, but its amplitude was 1. So when I put a 2 in front, the sine curve just looks, I'm trying to exaggerate a little bit, in that it's a taller curve. At 3 pi over 2, it still goes down to about a negative 2, and at 2 pi it comes back again. So the period was still 2 pi, but the height difference because of this 2 changed. All right, let's try this again now. So what we're going to do now is we're just going to put a number in front of the variable x and see how that affects, and I'm going to put here, affects the period of the curve, and it will affect the period of the function. So I have chosen to start with 0 radians, pi over 8 radians, pi over 4. Those are different values than I did in previous work. We used pi over 6 quite a bit, and then pi over 3 and pi over 2, etc. So I'm just giving you more increments between 0 and pi over 2. Pi over 8 is about a 22.5 degree angle. Pi over 4 is a 45 degree angle. 45. This next one would be another 22 degrees onto the 45. So 77 or something. And then this would be 90 degrees. But we want to find the sine of 2 times x. So if x is 0, then 2 times 0 is still 0. And the sine of 0 is 0. But when you take this x value of pi over 8 and you multiply it by 2, it becomes 2 pi over 8, which is 1/4 pi. So take the sine of pi over 4 on your calculator, and you should get 0.707. And then here, again, we're trying to find the sine of 2x, but x is pi over 4. So when I multiply it by 2, I get 2 pi over 4, which is a half of pi. 2/4 is a half of pi. If you would take the sine of pi over 2, and maybe you remember from previously, that's a 90 degree angle. The sine of pi over 2 is 1. Again, you multiply this by 2, and another way to deal with this reducing is you could say 2 goes into here once, and 2 goes into here 4 times, and you have 3 pi over 4. So if you would take the sine of 3 pi over 4 on your graphing calculator, you'd get 0.707. Don't forget, in case you're not getting these values that I've gotten, your calculator must be in the radian mode in order to do this. Again, now we're at a 90 degree angle, which is pi over 2, but we're multiplying that by 2. These 2's cancel out, giving us pi. And when you take the sine of pi, we're already back to 0 again. So do you remember the repetition we experienced together as a group? 0, 0.707, 1, 0.707, 0. Now I'm not going to demonstrate the multiplying by 2 here. Essentially the 2 goes into the 8 this 4 times. And when you take the sine of 5 pi over 4, we're now in the third quadrant because 5 pi over 4 is more than pi. It's 1 1/4 pi. So you're in the third quadrant. So you're going to get a negative value for sine. And then here, when you take the sine of 3 pi over 2, you'll get a negative 1. And when you take the sine of 7 pi over 4, you'll get a negative 0.707. And when you take the sine of 2 pi, you're going to be back at 0. Okay, let's graph these ordered pairs. In an effort to give myself some space, I'm going to get rid of all of this right here. But what I want to do before we do this is I want to graph y equals the sine of x on my paper, if you will. And so I'm going to try to stretch this out as long as I can. And I'm going to scroll a little bit. So please remember that, and I'm going to stretch it a little, when x was pi over 2, for the sine of x, just the sine of x, my output would be 1. Don't forget when x is 0, y is 0. At pi, I'm back to 0. At 3 pi over 2, I'm down to a negative 1. And at 2 pi, I'm back to 0. So the regular sine curve, sine of x, looks like this. All right, but what I want to do now, see all these values for x right here? I want to graph this through all these output values, but do you see how my value for x is pi right here? And when I multiplied it by 2, I got 2 pi, and the sine of 2 pi was 0. These values for x right here, I'm even going to erase some of what's on here as well so you can see it now. I'm going to go through here and graph with these x values, these outputs. So when x is 0, y is 0, and I'm going to do that in red. When x is pi over 8, I get 0.707. And so in order to determine where pi over 8 is, pi over 2 is right here, and I've got 1, 2, 3 increments in here. So I'm going to put a tick mark right here. And so this would be pi over 8. This spot right here would be pi over 4. This spot right here would be 3 pi over 8. And then here I am at pi. So let's go back to the red ordered pairs. When x is pi over 8, y is 0.707. That's about right there. When x is pi over 4, y is 1. So right here, the sine curve tops out already. For this curve where y equals the sine of 2x, not just x, but 2x. When x is 3 pi over 8, I'm at 0.707 right here. And then when x is pi over 2, I'm back to 0. So look at the graph of the red equation, which is half of a sine curve already. It's half of the wave. So what's going to happen because of this too is that the period of this curve is not going to be this large anymore. It's going to be cut down. It's going to be shortened. Let's keep going. So right here I've got to divide this into 4 equal increments and see this pi over 2. This spot right here would be the 5 pi over 8. This spot right here would be the 3 pi over 4. And that spot right there would be the 7 pi over 8. And then let's put the red dots in. So at 5 pi over 8, my output is negative 0.707. So about right here. And at 3 pi over 4, it's a negative 1. And at 7 pi over 8, it's a negative 0.707, and then back to 0. I am going to label this value right here as a negative 1. And so I see this curve finishing up. So here is this curve finished up in half the time. So the period of this function, which is called y equals the sine of 2x, is now pi instead of 2 pi previously. I'm going to stop here and I'm going to ask you to explore in our next video.